time for us to start the Western Hemisphere Virtual Symplectic Seminar with a speaker who is not from the Western Hemisphere. So it's a pleasure to have Marcy Robertson, who will tell us about expansions, completions, and automorphisms of welded, tangled foams. Go ahead.
Well, thanks everyone. As happens when you send a abstract, then you go back to write the talk that matches it. I reread the abstract for this, and it was way too ambitious, and so I'm really impressed that you turned up. So thank you very much. And I simplified greatly, but let me. So I should start by saying this is joint work with Juji Dansho in Sydney and Iva Halacheva, who's at Northeastern. So you know, if you need follow-up, Ava's in your time zone a bit closer. So I have two goals today, which are to tell you about how higher dimensional tangles, so surfaces embedded in R4, sort of naturally are the morphisms of a tensor category. Okay, so, and I will define everything about that, so it's not a big deal. And the second part is to provide some motivation for why you would consider doing this, right? The idea is not just to make a category because it's fun. There's actually like a problem in the background that will make this really useful. So I'm going to start from part 2, and so the first couple of slides will be a little bit broad overview, and then we'll drill down into some definitions here. Okay. So our motivation, see if this all fits. So my motivation, you could pick a lot of ones, but I decided to pick sort of topologically motivated things. So let's say you wanted to take a class of knotted objects, tangles, links, braids, etc., and you wanted to consider universal finite type invariants, or we'll just, I'll use Juji's word for this, expansions. So what is this? This is an invariant. You take input, some kind of knotted object, you construct an invariant like the Alexander polynomial or something, and you land in some graded space where you can actually do your computations. All right, so this allows you to distinguish knots, etc. So a couple of these happen to have implications in quantum algebra. So in one example of that from Barneton in '96 is that if your knotted objects are braids, and they're in quotes because I actually mean parenthesized braids, but we're not really going to talk about them. So I'm just putting them in quotes. So braids standing in for regular knots. The existence of such an invariant is equivalent to the existence of a Drenfeld associator. So this is something that naturally arises in quantization. And in fact, Barneton arrives at this correspondence that expansions of braids are in one-to-one correspondence with associators, Drenfeld. So like the set of such expansions is equivalent to the set of Drenfeld associators. Okay, so why might this be cool? What might be a motivation for this? So one thing is that the set of associators have these really beautiful groups of symmetries called the Grothendieck Teichmüller group, or the graded side. Get my little laser pointer guy. On the graded side, right, so remember these are maps from knotted objects K, right, to some A. So on the graded side, you have this GRT, and on the non-graded side, you have this group GT, and they act freely and transitively on this set of associators. Right? So associators are torsor. Why might that be cool? If I say you give me one such set, so one such homomorphism, the groups GT and GRT have really nice explicit descriptions. You can write out a presentation, and I'm happy to do so at the end of the talk if someone wants to see a presentation. And so I can just act by GT and get myself a new, I can pre-compose with GT, get myself a new invariant, or post-compose with GRT, etc., to find a nicer way to compute. Right, so this situation, I always add in purple the references on the side. So this is Drenfeld in '91. I should say that my actual motivation is not the knot theory. I'm interested in there's a pro-finite version of this case, where the absolute Galois group of Q, so a very central object number theory, lives inside of the pro-finite Grothendieck Teichmüller group. So I'm interested from that point of view, and I'll tell you about that in some other context. But there's a sort of, as this rise in knot theory, this is one motivation. And our focus today is, we're going to talk about a higher dimensional version of this. Some of you might have even seen either Juji or Jor talk about this. It's been around since 2016, but let's say that our knotted objects now are something very specific called welded tangled foams. So these are embedded surfaces in R4. I'll give a definition in some sense. And I want to look at expansions. Well, in fact, expansions of these objects, so Jor and Juji repeat sort of the idea of Jor's paper in 96, is in fact they're in one-to-one correspondence with something called the solutions to the Kashiwara-Vergne conjecture. So this is a conjecture in Lie algebras, which basically asks, given e to the x, e to the y, right? So in a non-commutative context, can you write this in terms of, and there's actually something, but two convergent power series instead of the usual Campbell-Baker-Hausdorff series, right? So you're looking for such things. I'm going to put that in quotes because that's also, there's some coefficients there that need to be there. But anyway, that's the basic idea of this question. So it seems like it's completely random, but it's corresponding to these knot invariants. Okay. So what is our goal? So, sorry, a little bit more detail. In fact, it turns out that the general solutions to the Kashiwara-Vergne problem also depend on the existence of a Drenfeld associator, right? So remember that I'm saying that the existence of an expansion for braids, for parenthesized braids, this comes from the existence of a Drenfeld associator. The existence of a solution to Kashiwara-Vergne, and therefore the existence of an expansion for welded tangled foams, comes from a Drenfeld associator. And the references there are these papers by Alexiev and Tarasian and Alexiev, Enriquez, and Tarasian. I recommend. This paper is really easy to read, and the other one gives me like a migraine. So somehow same problem, but different notation. Let's put this all into a diagram, which will come up in the talk again. So what happens here? Okay, so we have associators, and these are corresponding to expansions of braids, right? So knot invariants for like classical tangles knots. And GT is living down here. Up here, I have a four-dimensional topic. So I have surfaces embedded in R4. And solutions to the Kashiwara-Vergne equation correspond to expansions of this four-dimensional topology. And there happens to be a map U, so this is in the AET paper, that takes associators, like it generates a solution from Kashiwara-Vergne from a Drenfeld associator. But these are fundamentally different spaces, right? This is two-dimensional knot theory on the bottom row, four-dimensional knot theory on the top row, right? Or if you want to think about it algebraically, these are solutions in the Drenfeld-Kono-Lie algebras, so infinitesimal braids, and these are solutions in free Lie algebras. So this is not free and this is free. So there's something going on there. These are somehow very different spaces, and yet they're deeply related. So my goal with Juji and Eva is to sort of give a topological understanding of what's going on in this problem, and to get an explicit relationship between the associators and solutions to KB. So what we'll be talking about today is a small piece of that, which is about providing a formal language so that all the objects in this diagram now live in the same place, right? I want to give a place so that I can actually describe what's happening here, like the sort of universal language for this diagram. So this becomes a diagram of categories, or they're slightly fancier than categories. And these morphisms are functors. basically. And so I can actually study this problem, and the long-term goal is to understand this image of U. Is every solution to Kashiwara-Vergne from a Drenfeld associator? Is it not? Okay. So I know that was a rapid introduction to deformation theory and quantum algebra, but I wanted to give you a point that I'm going to do something abstract here, but it comes from a real place. Like I have a motivation for it in order to set everything in one context. Okay. So now let's take this down to some really basic ideas. So I'm going to introduce to you a setting for these welded tangle forms and expansions. It's kind of abstract, and I want to start with something that many of you may have seen before and maybe have not. So we'll start with planar algebra as a way to think about tangles. All right, so what's a planar algebra? So it's just a sequence of vector spaces indexed by the natural numbers, together with a family of linear maps. So here, which basically tell me how to multiply, to tensor up a bunch of vector spaces where that parameter is given by a tangle, a planar tangle. And so this is an embedding of a one manifold into a disk with holes in a nice way, right? So here is a tangle, T, K1, K2, N, so of type K1. So here, this is T4, 2, 6. So here, the hole marked 1. So the one manifold here is purple. That's sort of just giving me a thing, an element. So this is basically saying that this is a multiplication of some vector space indexed by 4. I'm multiplying it 2, 2 to some vector space by 2, and it lands in some vector space indexed by 6. But this multiplication is specifically going to be given by this little wire here. Right? So it's just a way of parameterizing tensoring. Okay. And in fact, we want a little bit more structure on planar algebras. We want them to have, we want them to respect tangle composition. So you can iterate tangles, right? Which is nothing too fancy. It just means that I can shove one tangle. Sorry, this doesn't, there we go. I think that doesn't quite fit. So basically I'm saying that if I have a hole in my planar tangle, like this one, which is indicated by a 1, and I have on it marked boundary points, into 4 boundary points. If these 4 boundary points match up, well, then I can just glue this thing. I can line up the one manifold can line up, and I assemble into a new tangle. So that's a type of composition. And I want this to induce a composition on my vector space maps. Okay, so here I have, again, this just random multiplication. So I'm saying that S is this guy. This is S. Let me give it's a good color. Purple's a good color. So here's S. So S is giving me the tensor product, VM1 tensor VM2 into VK1. And T is giving me VK1, VK2, VK3. And I can just simply map this, identify this vector space with itself. So just regular linear composition of maps. And I land in this weird tangle over here. So this other map. So I want that to be a property. If you're familiar with this, you can also just say that the planar algebras equals a algebra over an operad of planar tangles. Right, that's composing, it's just saying that the action of this, an operad is just like a really ugly non-commutative algebra, and it's acting on a bunch of vector spaces. Right. So I'm not sure why I included the maps. So anyway, I'm a homomorphism of planar algebras. is again going to be like something that family of maps from these family of vector spaces that commute with my tangle option, with my tangle action. I don't actually think we use that, so that's an extraneous slide, but there you go. All right, so here's an example from low-dimensional topology. So, right, it's not just sort of algebras, but there's a way to think of classical tangles. So tangles themselves are a planar algebra. They have an algebraic structure. I believe this is also due to Barnaton, and I don't remember the year. I'll try to remember before. I think that's correct. So classical tangle, so right, this is a smooth embedding of an oriented one manifold, just to, so that we all have our same definitions, into B3 where the boundaries are preserved and it's considered up to boundary preserving ambient isotopy. As a planar algebra, I can write it as this presentation. I'm going to say as a planar algebra, all classical tangles are given by the planar algebra with these generators, so over and under crossing, and up to the 3 Reidemeister moves, and these are relations. Okay, so an element, in other words, an element of this algebra will be a tangle. So let's look at an example here, right? So here's a tangle that I've hopefully drawn correctly. So here's my my tangle, and I want to see this as being like coming from being an element generated by these things. So it's kind of a now obvious idea. Well, I look at these crossings. Right. So I can really have pulled this apart and be, well, okay, so I know what the tangle operation is on this. It comes from, I'm going to draw this kind of bad. So I have my 3 things. I've got my wiggle, got this guy. Say there's some wires there. Anyway, I have some wires there, and it acts on, well, over, that's why I pre-drew, because I can't draw. You can tell what kind of topologist you are, I think, based on if you can draw crossings. I'm not this type. Right, and that goes to my, original tangle. So you can write somehow each element of tangles as an element of planar algebras. Okay, so this is in the background as something that is useful.
I'm sorry, can I ask a question?
Yeah, please do. Dive in.
What's happening with these extra components that are on the right that you didn't do anything with? The circle.
So, yeah, so those things are a feature. These like embedded loops or something. So these are a feature of the fact that, right, I'm being acted on by these tangle operations. So it's actually like a subtle point. So good question. So I'm including these, remember, in my tangle diagrams that act on planar algebras. So where was my, like this guy? This is like an element that acts on these inputs. Now, if you wanted to include those loops as algebraic operations, you could modify this structure slightly, actually. So you have a choice where you put them. The weird thing about these sort of free-floating circles is they don't contribute any algebraic data, so I've decided to leave them out. But you could, in fact, modify this structure. I guess it would be closer to the structure we're going to talk about at the end today, the circuit algebra or wheeled prop thing, where you can close up loops to make circles if you would like to include them. Yeah.
Thank you.
Yeah, no problem. But yeah, the sort of von Jones version of planar algebra just has them floating around, not doing anything. I hate the little circles. So as the more algebraists in our collaboration, I'm very irritated by these things. All right, great. So now, because they don't do anything, but they have to be there, it drives me crazy. So W tangles. So we can talk about this 4-dimensional one. These are embeddings of framed surfaces. I think framed is optional, but I only understand it with the frame. So if you're framed surfaces into R4 up to ambient isotopy. And so, oh, my planar disappeared. Had a cat assisting with writing this talk. So, to classical tangles, there's, oh, there it is. Yeah, the PL moved down there. Anyway, there's they form a planar algebra. So here's the presentation as a planar algebra. So here I have my, now when you're in R4, you have things that can pass by each other. And now if I project down, like you do the Reidemeister theory, I obtain these virtual crossings. So these are just, they're just drawn as X's, but it's things that are sort of passing by each other and then projected into the plane. They look like they're directly on top of each other. Whereas these over and under crossings, right, these would now be like tubes passing through each other in R4. Okay, and so I now have 3 generators here and a bunch of operations. So here, these are the standard Reidemeister moves. This is the framed R1. And then I drew some of them. There's virtual Reidemeister moves for these virtual crossings here. So like, for example, you have a virtual R2, which is exactly like regular R2, but with virtual crossings. And then you have a mixed, how they interact. And then you have this OC, which is over crossings commute. I should say that if you are, there's also a virtual tangles version of this. So these are then embedded one manifolds in thickened surfaces. These are sort of the same without OC. Maybe to put that in like math, WT equals VT mod OC. So you add an extra operation. They're very different geometric objects, but they have similar presentations as a planar algebra. But that's only if you're sort of curious about why I'm skipping the virtual case. So let's look again at what one of these might look like. And I put some references. So for the virtual stuff, I learned it well from this survey article by Kuperberg, What is a Virtual Link? It's also mentioned in this Barnaton and Doncho paper. And then if you're coming from the more physicsy side, the W braids, like as opposed to W tangles, they're also called loop braid groups by Baez. So you might have seen something like this before, right? So what is this? What are the differences in this feature, right? So note that now here I have virtual crossings. I can just sort of basically I've switched from an embedded to an immersed one manifold, although I'm still thinking of this as a planar algebra. So these would be generators. It would be a generator and so forth. And I didn't draw the arrows or anything like that. So these would be, I could write this algebraically by just sort of isolating the features, and then I can write it as a multiplication. Okay. So I'm going to start a little bit of a transition. This is in some ways kind of a heavy-handed idea, but it's certainly a nice algebraic way to encode your knotted objects. And oh, I can see it. Good, Ava's on the chat, so you can ask all topology questions to Ava. I'm just kidding. Hey, Ava. So I'm going to switch to a sort of more reasonable, or in my opinion, more reasonable way to think about this that's more natural. So these virtual crossings are kind of strange. They're basically just transpositions. And in fact, in knot theory, there's this notion of the detour move for virtual crossing that basically say that these virtual Reidemeister moves are pretty trivial. You can move them around. So this led Barnaton and Donshaw to design circuit algebras. They didn't want to think about the virtual crossings, they moved them. And so just to tie back to our original idea, well, remember we're looking at expansions. So what were these finite type invariants? Okay, so these expansions are now actually just homomorphisms of circuit algebras. So now if you give your, and I haven't explained what the tangled foams part, but just so if you just look at the, I haven't explained the F yet, but a homomorphic expansion or is from W tangles to some graded space, and we have to add something to get to solutions of KV. These are in fact just homomorphisms of this algebraic structure. Okay. So, and if you want sort of the details on this virtual thing, it seems to be in this Dye-Kaufman paper. That might not be the first source, that's just the one I'm aware of. Okay, so let's go back to our motivation. All right, to replace ourselves in the talk. So we're looking for a formal language in which we can set this whole diagram here, right, where we have some groups of symmetries, KV and KRV, some expansions of parenthesized braids or Drenfeld associators, and expansions of W foams. So these are WT plus something, right? And like that, we want to set this all in the same language. Okay, so down here, braids and classical tangles and things, these are planar algebra. Up here, I've just described that these could be a planar algebra, but it's somehow not a particularly good way to deal with it, and particularly for expansions. So I want to put them all in the same language. All right, so I'll state some theorems. And then, the first one is already appeared. We wrote a small paper for the formalism, and the second one is on its way. So the theorem is that we can in fact figure out that these circuit algebras are a type of category, which I'll explain to you, called a linear wheeled prop. The second is that, in fact, this is a formal language that we can use to write down that these groups of symmetries here are automorphisms of a completion of this now prop of welded tangled foams, and that the graded side is, I'm not talking about the graded side, but it's this object will be a type of category whose morphisms are weird Jacobi diagrams. All right, so what are we actually gaining from this? The implication is that all the objects in the diagram are homomorphisms or automorphisms. So I'm talking now about homomorphisms of some kind of, so functors here from some K to A. I'm talking about acting on it by pre and post composition, and I can put the same categorical structure down here, and so this guy will be just a nice functor, right? Something I can study and really understand. All right, so just to remind you that there's a reason. All right, so let's give you a little bit of a definition. First, the topological interpretations, or just circuit algebra. So this is just like our planar algebra, except for we're no longer embedding one manifolds, we're going to take immersions. So I'm going to allow crossings like this in my tangle diagrams. I can slow down a little. All right, so I have a family of vector spaces, or just sets, if you want, together with a family of linear maps, parameterized by now wiring diagrams. So these are, let me write this as, these are tangles, where we replace embedded where we can immerse, I guess, the one manifold. Great. So in particular, every planar tangle is a wiring diagram. Planar algebras are in fact a subset of circuit algebras. Well, okay, every circuit algebra can be made a planar algebra. There's an adjunction there. But we are allowing these weird crossings so that we no longer have to include them as generators. All right, so let's unwind the structure a little and try to see this categorically. And then I'll come back to the welded tangled foams in a second to show you what it means. Okay, so I want to give you a definition. So this is a linear prop. So now I want to talk about categories. So this is a tensor category. So I have a symmetric monoidal structure on a category whose monoid of objects is single generator. All right, what does that mean? Doesn't mean anything fancy at all. It just means that I have one, every object. So I have one object I've declared to be the generator X. Oh, that green is terrible. I've declared some object to be a generator, and every other object is of the form X tensor N, right? Where if N is 0, then that's the unit. Oh, sorry about that. If N is 0, it's just the unit, right? So I just have like one object and I just tensor it up over and over again. And in practice, what does that mean? Well, that means the morphisms are going to be of the form, right? So I have every morphism in the category will be say something like f from x squared to x cubed, right? Which we draw graphically as, well, we take a graph. This is a vertex. It kind of looks, it specifically looks like the tangle diagrams on purpose, but I have a graph. And I've now just colored my inputting edges with X. So this would be like X tensor X, and then X tensor X tensor X. All right, so I'm just thinking, I'm just picturing the morphism this way. And you have this here, okay? And this is the original definition, this McLean, so categorical algebra. This is from the 60s or 70s or something. Okay. So the fact that P is a category, so let's just see a little bit more what the structure looks like, means that we have composition, right? So here, if I composed F and G, that means if I have, inputs, I glue them to an output. It's now, right, they're not somehow like just input wires, they're objects. So I'm composing along an object. And in the literature, this is called vertical composition. I drew it vertically as a sort of thing. And it's just categorical composition, just regular composition of objects. Okay, and the fact that it's a tensor category means that we can just, when you tensor morphisms, you just stack them next to each other. So this is called horizontal composition in the literature. Which I'm just saying that here, if I have, I've taken this morphism living here, so P from 3 to 2, so that should be X third. It just looks kind of sloppy after a while. So X times 2, that's what that means. I just wrote the coefficients. And then I tensor with a different morphism, then I'm just gonna land with something, I've just stacked them next to each other. Okay, so that's all that's happening there. It's just the product. So disjoint union of maps, that's all that's happening. Okay, a wheeled prop, the object of our sort of theorem, as I'm going too fast, is what's called a rigid object. So this comes from Tanaka duality, but so rigid just means that every object has a dual, like a vector space dual. And this means in practice, what this means is that we have, this gives trace operations on our category, right? So if I have an X and an X dual, then I can identify them. So this would be like the trace of this. So 1, 2. So here's the, I don't know. You would label these guys and you would identify them. So it allows me to contract things. So earlier when you were talking about these loops that are floating around in the connection diagrams and the tangles, you could obtain them this way, right? So yeah, this is a definition that's relatively new from 2009. And there's a nice survey about how these arrive in sort of BV quantization by Merkulov. So normally these are things that I've only seen up until this point, working with Iva and Gigi. These objects kind of arise as in deformation theory. Okay, but they're perfectly nice categories. Why not? All right, so now let's look back at our key example. All right.
Sorry,
So yeah, please. I'm definitely going too fast, so interrupt me.
Does the words vertical and horizontal composition imply that there's a relationship with two categories?
So yes, so I have this like weird terror of two categories that I probably shouldn't have as like a homotopy theorist. It's probably not allowed, but so yes, a prop can be thought of as a two category, and there's they have this. Why am I blanking on the word? They're compatible in precisely the way you need to have these two compositions interact. They're bimonoidal, I think is the thing. So yeah, a prop is a two category. I think that's a known fact. Yes, in fact, it was written up by a collaborator of mine, Donald Yao, some years ago. I don't think anyone's ever thought about wheeled props with the, I don't think that would be in the literature, that when you add the trace that it's a two category. It certainly would be, as long as I have actually made people promise not to make me write that down. But if I ever have a student I really hate, I'll have them write that down. No, I shouldn't say that, because then what happens when the thesis comes out? But yeah, so they certainly are. And if you're familiar with the planar algebras literature, right? So a lot of times people think of planar algebra as these like pivotal or fusion categories, which are, they want this to be an equivalence of two categories. There's quite a lot of work on that regard. This would be an equivalent statement if you wanted to write down the two category part. So the theorem could be elevated to an equivalence of two categories. Right, so back to our example. So, okay, we have got our, I sort of jumped the gun on the phone. So the welded tangles. So, okay, remember I gave this presentation as a planar algebra, just to sort of emphasize what the difference is here. As a circuit algebra, I now just have a really simple presentation. I only have the crossings and the Reidemeister moves, R1, R2, and R3, right? Because here, these are the generators. But these are just parts of the immersed connection diagram, so I can sort of ignore them. And what I'm thinking of as like what I'm thinking of as the way this works is, right, these purple, the one manifold, are really just indicating objects or parts of objects in the category, in like a category. And they're really just labels. They're somehow abstract. This is a completely combinatorial definition, actually. Like you have once you've passed from an embedding to an immersion, you can pass basically a completely abstract combinatorial object. And so these are just like objects. And this then is just a transposition of objects. It's sort of hidden in the structure. I can permute the tensor powers of my objects. So, so like that, while it is a topological feature, it can also be abstracted away and you don't lose anything, which I think is kind of cool. All right, so now you've really reduced your presentation. So that's always a positive thing. If you're going to do some algebra. But now I want to get back to the main goal. Maybe I should say. This maybe should have been. And so now if I have this WTF, which I think it took me a long time to realize that that was also a joke of Gigi and George's. And it also makes a lot of sense algebraically. That's a joke. I'll just say that. But so what is this? So I want to extend my structure a little. So I have my tangles. So these are just tangled surfaces in R4. But I'm aiming for this relationship with quantum algebra, and you need something. You need an associator. You need to see an associator. So this actually comes in this thing called a foamed vertex. And sort of a question for the audience, if anyone knows, I've seen sort of the notion of foams in like when in extensive Googling arise in like the context of cognitive homology, but I don't know if these are the same foams. So I'm happy to, if this looks even remotely familiar, let's chat. So what is a foamed vertex? So it's kind of a half crossing. So in our embedded surfaces, so my drawing is going to be really bad. So if you have, you know, a couple of tubes, say this is passing through, right? This is going to be, this is what I'm writing down. And maybe I got that backwards, but I'm writing this down as a crossing. So they're literally passing through each other, right? If they're passing past each other and not intersecting, that's one of those virtual crossings. It's not really an interesting topic. So what a foamed vertex is when two tubes sort of, one flies inside of another and they fuse, right? So maybe not officially, but they like stick together, right? So I've drawn badly this sort of flying rings picture. So here we're like the tube entering is the blue tube. I'll try to. I guess the red one should come first. So I've got some tube of the surface. And here I can have the blue tube enter. So here, but it doesn't exit, it just kind of carries along. So there are a variety of ways in which this can happen. I think if you take every orientation, I think there are 6 of them, give or take, and you add these to your structure. So combinatorially, it's just adding generators, but topologically, it's adding a whole kind of weird behavior, right? And of course, there's an even weirder thing in the sense that, like, if you have, you can push them off each other. That's why I insisted on the framing. So you can have behavior like this, right? So I can compose 2 such fusings. So here, this is where I have like I have a tube that splits into 2. This is one possible vertex. I'm not sure if that's clear. Let me know if I need to redraw the picture. And this is one where the tube is going in. But in this case, then I can actually pull them apart. It's called an unzip. So there's this little data over here. So what this is this part here, up until I have this ... right? So this is telling you, well, I've added here to my welded tangles, so W tangles. I've got these 2 crossings, it's a normal tangle structure. I've added these half crossings, these fusings. I've added a cap, which just means I can cap a tube, kind of take the tube out of context. If you're familiar with the way that this sometimes happens with braids, when they compute knot invariance, they like to delete strands, etc. So it's this kind of thing. So this is a cap. And then I have the Reidemeister moves. This is the cap pull out, so that if I've capped a tube, I can basically, you know, I can kind of get it out of the picture. I've really deleted the interesting part by that's the relation CP. And R4 is sort of how the vertices interact with the crossings. Now there's dot, 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 is that these things actually, because of this weird extra structure, these foamed vertices, I have operations to my algebra structure. So think of it like if you have a inner product space, it's a vector space plus an inner product, right? So this, right, it's not part of the vector space data. That's sort of this unzipped guy lives there. It's not so much a part of the algebra as a an additional operation, which is, as far as I can tell, entirely topological in origin. This makes no sense as an algebraist at all. So it literally has to come from the fact that these are topological objects, as far as I can tell. Okay, so now I'm going to give you a really simple proof theorem. So these circuit algebras, they are in one-to-one correspondence. There's an equivalence of categories between this and linear wheeled props. And here's the proof, right? So here I've taken my, just one of these wiring diagrams, and one is in purple,